Thank you. Hello, everyone. With Jeremy and Bharathi, we present transitioning the Cisco main compiler and toolchain to LVM. Here's the outline of our talk. You start by briefly introducing networking software and the role of compiler. Then we'll describe our code base and contributions to LLVM backends to ensure that our software runs on all processors we need. Then we'll present all steps needed to deliver best runtime performance with Clang on key data plane component. We'll continue with our work on compiler and tool to deliver solid debugging experience, and we'll conclude with our practice with the Clang program analysis, sanitizers, and static analysis. Enterprise networking is a huge market with products such as switches, routers, access points. Each box includes multiple CPUs, ASICs, FPGA, or network processors. Product lifecycle typically extend many years, working 24/7, so the typical reliability of networking device is much higher than that of personal computers, for example. Products deliver many exciting networking and security features, including routing, availability protocols, management, provisioning, and recently data collection and analysis. The networking software that usually runs on a device is called Network OS. It has many different multi-process, multi-thread components. For example, Cisco IOS XE architecture include embedded Linux kernel, different modules, common subsystems, hosted applications, databases, and so on. In terms of the workload characterization, not much IOP, mostly single thread optimization for throughput. And compilers optimize individual components differently. For example, components that are closer to the hardware are optimized for runtime performance, and you talk about our work on tuning data plane component for that, while higher level components are optimized for code size. And of course, security and debuggability are important too. One interesting or unique feature of networking software is the mismatch between network byte order and Little Indian order in most common computers today. Nearly all networking protocols are defined to be Big Indian. So ideally, a programmer will insert conversion macros immediately before sending, immediately after receiving network values. However, there have been a lot of code that is written as Big Indian in times where processors were Big Indian or written for high performance. So compiler can help resolve this byte order mismatch in several ways by compiling Big Indian code to execute on Little Indian processors, or reducing number of reordering instructions to improve performance, or helping rewrite Big Indian code into Indian neutral one. Software for networking by its very nature present many testing and debugging challenges. Any realistic testing typically requires a very dedicated, distributed, and expensive test beds like the TurLab shown on the slide. Multiple nodes, distributed locations. The compiler and runtime, therefore, needs to generate high quality debug information, very focused trace information in order to remotely triage some subtle issues, for example, low network performance or packets dropped. So in summary, networking software is very complex and compiler can play a big role.
Okay, I'm Jeremy. I'm going to be talking about our Cisco codebase and the contributions we've made to LLVM to support our various backends. So as Ivan mentioned, we have quite a large codebase, our networking operating system, 3 different major ones. We run everything on top of the Linux kernel, and on top of that, we place the open source software and our proprietary source code. And most of it is written in C. We have quite a wide variety of architectures that we're using on our hardware, x86 and ARM mostly, but also PowerPC and MIPS. One thing that's very crucial for us is all of our software is built with a very high optimization level. So normally everything is going to be built with O2 or O3. We started the journey to LLVM in 2015. The main driver for our initial adaptation, and thanks to Scott, who is here in the audience, who did the initial work, was we wanted really to be able to write business critical features in an easy manner. So we found that LLVM really allowed us to write some of these initial features that we needed much more easily than GCC did. And of course, we also can use the wonderful bug finding ability that LLVM has, things like sanitizers, fuzzers, static analysis, and compiler warnings. So currently, we're working on migrating to 7.0 across our code bases. So one of the architectures we use is MIPS, and we found some challenges there. First of all, we found that the LLD support for MIPS was not as good as we found in binutils. So we are currently still using a hybrid model where we use LLVM as compiler and binutils as linker for MIPS. We also found that some of the MIPS-specific features are committed directly into GCC by the MIPS vendors, and a lot of those features are not co-committed into LLVM. So in some cases, we found that instructions were missed or key optimizations were not done, and we found a performance gap between MIPS on GCC and LLVM. So that's an area we're really trying to improve on, and here are a couple of submissions we've made to the community to improve MIPS support. PowerPC 32 is an architecture we use on quite a number of low-end devices as well as some high-end routers. We found that we had trouble with LLD on PowerPC 32, so that's an area we'd like to work on and improve. When we initially loaded the PowerPC 32 image built with LLVM onto our devices, we found that the processes were immediately being killed. And what was happening was the modern Linux kernel expects that these PLT sections are security protected so that they're not executable. And we found that LLVM was incorrectly marking these sections. Well, LLVM plus the binutils linker were incorrectly marking these sections as executable. So we realized that LLVM was missing a key feature called msecure PLT that GCC supported by default. So what this feature does is it generates the right relocations to tell the linker that the PLT section needs to be marked as non-executable. So basically all the symbol table, the functions, and the TLS variables need to be marked up with these relocations. So to give an example of what the code looks like without this, without these relocations, here's a very simple example where we're just calling a libc function with a string. If we don't pass the msecure flag, we see that the relocations are just direct into the string or the function, and they're not relative to the GOT. Whereas once we've added this secure PLT flag, we see that the relocations are being corrected, and now the linker knows to correctly generate the secure GUT section. So these are some of the contributions we made to LLVM to enable the support. And now once we've submitted these, we're able to correctly fully build our system on PPC32 and load it. So with this feature in place, we're having great success with PPC32 now.
Seshadri, and I'll be talking about our experience migrating the data plane application to LLVM. So the goal of data plane is to forward packets with high throughput and low latency. Performance is very crucial. We have x86 and ARM targets, Little Endian and Big Endian variants. Currently it is 32-bit, and we are moving to 7.1. So the initial steps where we had to handle some compile time issues like replacing externally visible attribute with used and adding some option in the gold linker which was required for ARM Big Endian build, and fixed a number of errors and warnings because we have WAL and WError enabled. One of the painful runtime issue was due to unaligned access. So both ARM and x86 have certain instructions that expect aligned addresses, and if the address is not aligned, like 4-byte align in the case of LDM and STM instructions, then they will lead to a runtime trap. So in our case, the incoming packet buffer is just a stream of characters. It has no alignment guarantees. We just cast it to whatever structure is needed without making expensive local copies. And if such alignment expecting instructions are generated to access those structures, then it will lead to a runtime crash. So one can argue that these casts have to be fixed in the source code, but the challenge is how do you find all these places in the code that need to be fixed at compile time. So let's take an example. In x86, we have a case where there is an array of 64-bit values that is tagged with a line attribute having 16 bytes. And the two consecutive 64-bit stores are rightfully optimized by the optimizer into a SSC 128-bit move instruction, move DQA. So in this case, if buff is not 16-byte aligned, then the move DQA will trap. So the question is, how do you find these kind of, so if the alignment attribute was not specified, or if memcpy was used to do the stores, then the compiler would have generated move DQU, which expects no alignment, and everything would have been fine. So how do we know what to fix and where to fix? We tried a couple of steps. So first we started off with using wcast align option. It helped a little bit, but there were just too many warnings that it was not very meaningful to pursue that. Then we tagged all the structures involved in packet align, in packet processing as packed, so that the compiler cannot have any alignment requirements. We even had align types for UN32 and UN64. Then it was not still enough. And then we try to see if we can kind of avoid generating these problematic instructions. So one option was to turn off the ARM load store optimization, which was too aggressive. Then with 4.0 came the ARM assume misaligned load store option, which is less aggressive. And then we still found that there were some problematic cases where memcpy was expanding to LDM STMs, and that had some issues as well. So we just tried to suppress that. In the case of x86, for both aligned and unaligned instructions, for most modern processors this is true, that there is no difference in performance if the address is aligned at runtime. So whether you use move DQU or move DQA, there is no difference in performance. So on this basis, we implemented an option, gen unaligned, to generate the unaligned instructions instead of the aligned counterparts. Lastly, reliability is more important than performance. So our network engineers implemented a user-level fix-up handler as a safety net to catch these traps at runtime if they arise and log the offending instruction and then fix the exception. So this way, the router will not crash and there will be a performance cost to doing this, but hopefully these are very, very rare because almost all of them have already been taken care of. Another optimization triggered bug was there was a IP header corruption that was observed when the struct assignment was executed. What we observed was the two structures had overlapping memory, and this was optimized to a memcpy intrinsic. Because memcpy does not handle overlapping memory, it's not expected to. So this resulted in a corruption, and we fixed this in the sources using a memmove instruction. We also ran into a number of issues around inline ASMs that were that required rewriting the constraints to make sure the output operands were not overwritten and specifying the clawbars. The challenge was mainly in identifying these places when we ran into runtime issues. We fixed a couple of problems in atomic intrinsics as well. Coming to performance, we use instruction tracing and perf to monitor and improve the performance of data plane. So when we ran perf, we found that memset was one of the top 20 functions, and that was not desirable. So it was partly because a lot of the memset intrinsics did not get lower to the stores, but a call to memset. So we increased the threshold to tune the max stores per memset from 8 to 16, and that gave us a gain of nearly 8%. Similarly, there is a function to read thread pointer from coprocessor register. This is a function call, so we implemented an option read TP hard to directly read this thread pointer from the register, so there are no calls to this function, and this gave us a savings of 57 instructions per packet, leading to a 2.6% gain. So we've always been using LTO for data plane, but when we use Clang LLVM toolchain, we were able to compile more data plane features with the FLTO option without breaking the bills, and this gave us an added gain of the order of 10 to 15% over our LTO gains. We are experimenting with thin LTO as well. We get faster bills and we observe less memory usage, but we ran into some degradations on our key benchmarks. We do not have profile data, and a lot of our sources are tuned with always inline and no inline attributes. And what we found was thin LTO, the function importing does not handle always inline, so some of our key always inline functions got missed. So when we increased the threshold, it did improve the performance, but I think when we fix the function importing to understand always inline, we should be in a position to adopt thin LTO successfully. So overall, Clang LLVM has proven to be very competitive and has met the needs of performance goals for a data plane. And on to the debugging experience by Ivan.
Debugging is very important in Cisco. All our builds are with .g, including release and internal builds. And we do remote live debugging as well, analysis of code files and associated backtraces. One example backtrace is shown on slide. And such backtraces are used to triage at first level and find bad component or bad function. However, if most of function parameters, values are optimized away, as shown in yellow, then any triaging is challenging. So 2 years ago, we found that debugging of optimized code in Clang is lagging behind that for GCC and ICC. especially over a set of code files we are getting from the field or internally, the percentage of optimized out variables in Clang was above 50%, while only in 35 range for GCC and ICC, as you can see in this table. So you set up to improve this bad situation, and we made multiple contributions to Debuginfo and DWARF support in Clang, beginning with enhancing Debuginfo for merge function paths, and our most recent contribution is recover, optimize out function parameters, which we present in LLVM Europe this year. Our analysis and our work is mostly driven by careful analysis of back traces, back to code files, back to builds, back to compiled passes, and figuring out what is missing and how to add Debuginfo support. And also driven by log stats reports. So log stats has been recently enhanced and contributed to LLVM, and it is very useful to report in a humanly readable way debug variables coverage. In this example, it shows coverage for formal parameters using GDB binary, and you can see 59% of all debug variables have full support, 100%. So that's good news. Back to our ongoing analysis of optimize out parameters and code files. We are very pleased to report that for the last 2 months of this year, the percentage of those parameters is down to 38%, and it's now very close to GCC and ICC. And it has been great collaborative work with community, especially with Apple and Sony PlayStation engineers to greatly improve debugging experience.
Okay, to finish our talk, I'm going to go over what we're doing for Clang program analysis. So in terms of the sanitizers, we've been using mainly LSAN and ASAN. We use a lot of proprietary memory management functions within our source base. So what we've done is tuned LSAN and ASAN to understand these functions so we get accurate reports for our memory corruption or memory leaks. We also typically only want to run these sanitizers on a small subset of the source base. Just to be able to load the image, we cannot typically instrument everything. So we've modified our build system to figure out the dependent libraries if we want to instrument a binary, just to make sure that we can just instrument one program at a time. In terms of memory leaks, typically we load our switches and they just run for weeks or months at a time without any downtime. So these processes are running just continuously. So since there's not a definite endpoint, we need to be sure that we can find the leaks anytime we want to. So we've actually added a CLI to our switches to do on-demand leak checking, and we're taking advantage of the built-in function in LLVM to do an on-demand leak check. Also, we want to make sure that if we do find an ASAN issue, that we continue after an error. So we use the ASAN recovery mode to find as many errors as possible rather than crashing immediately. In terms of static analysis within Clang, that's something we just started looking at. We're planning, we're using the Ericsson SA branch, and that's something we've just been talking about today at the static analysis, birds of a feather, but we'd like to use cross-translation analysis if possible because of our large code base, and we have typically dependencies across many files. So to get good results, we need to do CTU for SA. We actually had to write our own customized tool to do the CTU because we found that we weren't able to use Ericsson's code checker due to the system dependencies. We currently use a commercial static analysis tool, and what we'd like to do is continue to use that tool, but also try to use Clang SA as an enhancement to that. One thing we noticed was that whereas Clang SA was doing a great job on like an open source code such as GDB, we found that when it looked at our Cisco source code, it had a lot of issues with things like uninitialized variables. And we think that's because of the code patterns we use and the way we do error checking within our functions. So we're really interested in working with Apple and Ericsson and the other Clang SA maintainers to improve it and contribute to it and make it more useful on our code base. But currently we found that the commercial tool is finding a lot of issues that Clang SA didn't find. So that's our current feeling. This is just a small example of something that Clang SA was incorrectly reporting a uninitialized variable. If you look at the way the code flows, it's not possible that B is used uninitialized in this particular case. And our engineers are very sensitive to noise warnings, so we want to try to reduce them as much as possible. So now I'd just like to summarize. We've had great success switching our source base to LLVM. As Yvonne mentioned, our software stack is quite complex and has a variety of business needs with a wide variety of architectures and platforms, both low-end and high-end. We've really solidified the debugging experience for our users thanks to our contributions. And as Bharathi mentioned, our performance goals have really been met with Clang and LTO on our really performance-critical code bases. We feel that there's really a lot of opportunity to do more with LLVM. As I mentioned, LLD in some cases can be enhanced. We'd like to do more work with LTO, thin LTO, and PGO. And of course, there's a lot more opportunity to use additional sanitizers, HWASAN, more use of fuzzers, and really increase our static analysis use. And of course, we'd like to contribute more back to the community. So our final slide here shows the worldwide enterprising network software market share. And as you can see, Cisco has over 50% of that market. And since we're now building all of our software with LLVM, we can say that Clang is now compiling a majority of the networking software worldwide. So I'd really like to thank the community as well as all the folks, both inside and outside Cisco, mentioned on this page. So thanks a lot for sticking around to the end of the day to hear our talk, and we'd like to answer any questions you may have.
All right, we have time for maybe one question here.
Hi, great talk. I wanted to ask about your use of the sanitizers, especially for memory leaks. And just want to clarify, did you say you were running the code with sanitizers in production so you could fix the memory leaks as they were actually running on the customer's machines?
Yeah, so memory leaks, Eric, do you know that? Do you know the answer?
It's not in the production. So we have also enabled what we call image, which is mainly used for testing and development, but not in production.
All right, that's about all the time we have. Let's thank our speakers again.